Okay, today we're going to do our last chapter on logarithms, or our last topic on logarithms in chapter 8, and it's basically solving equations. So we're going to use logs and exponents, vice versa, to help us solve equations. So this is a complicated one on the title page, but basically what you can see here, we're using some log laws to do some conversions, and then we end up having to do some factoring and things like that. So we're going to look at an example similar to this a little bit later on. So basically, in terms of solving equations, there is no new material. We basically want to use everything we've learned so far to help us solve these equations. So here's a couple of tips. First thing is use log laws to change them into single logarithms. So if you get a question that has more than one log, so if I gave you log base 2 of 7, and we went log base 2 of 3, and that was equal to, say, 5 or something like that, we would use the log laws to put those together. So we'd combine the left-hand side to be 7 times 3 would be 21. So we get log 2 of 21, and I guess it wouldn't be equal to 5. It would be something like equal to x. So this would be a possible equation. So to solve it, we combine it into one log. So now we just have 2 to the x equals 21. We could solve that, or we could just leave it as a log and do log 21 divided by log 2. So that's sort of the strategies that we're going to be working with today. So that's how I would do that one. Go log 21 divided by log 2, and whatever that decimal is, you're done. So you want to combine the logs to get into one, and then the next thing you want to do is try to get your left and right hand sides either to be the same in terms of a log or an exponent, or we're going to usually change from a log to an exponent or vice versa. So this is a little bit hard to understand here, but what I'm writing here is basically, if you try to get your left and right equations to have the same log base, then the tops have to be the same. So for example, if we use this log 2 of 21 in our previous example, if that was equal to log 2 of x, if we could rearrange our equation so that both sides had both log 2's, that means then 21 would equal x. Okay, so if you can get both logs to be the same base, then the rest of it has to match. Similarly, we've already done this before. If I gave you something like 2 to the 4 equals 2 to the x, if our bases of our exponent equations are the same, then that means our left and right on the top part is also the same. And then the last one is if you get a log, change it to an exponent or vice versa. So if I gave you something like log 2 of x equal to 8, we could change that to be 2 to the 8 equals x, and then we could solve it from there. Or vice versa, if I gave you an exponent, we might need to switch it to a log to solve it back and forth. So you can use the conversion, but a lot of times you're just using the log laws to try to get it to be a log or an exponent on each side. And then also remember, with any kind of equation, we could also graph these. So if you're ever stuck or you're not sure what to do, it's never a bad idea to graph. So if I gave you some sort of weird equation, graph the left side, it might be a log graph that looks like that. Graph the right side, it might be something totally different, and our solution then would be where those two lines cross. So graphing will work. It's also good to be used sometimes to help you double check to make sure you got it right if you think you messed up. Okay, so let's basically go through a few examples to see what we would do. So our first strategy is get a single log. So in this case we got just a log form both sides, so that's good. Our second strategy is if they're the same, then that's good. So we have log 4 on both sides. They basically cancel them, or we ignore them. So that means 5x plus 1 has to equal to x plus 17. So now to solve it, subtract x on both sides. So we get 4x. Bring the 1 to the other side. It would equal 16. And divide by 4. And we're done. So x equals 4. And we could plug that back into the original to see if it actually works. So we have log 4 of 21 on the left-hand side, and on the right-hand side we'd have log 4 of 21. So obviously those are the same, so we're good. Okay, let's try another one. So this one looks a little bit different. We've got 2 logs on one side, and remember these are just regular logs, so we think of them as base 10. So let's combine those. We'd have log base 10 of 5x divided by x minus 1 because of that minus, so that's going to make it divide. And that's going to equal 1. So now we can actually use the crisscross rule. So let's change that to be 10 to the power of 1 equals 5x over x minus 1. Now we can solve this just by cross multiplying. So crisscross the 2 would have 10x minus 10. 5x times 1 would be 5x. Let's bring the 10x to the other side. So we get negative 10 equals negative 5x, divide by negative 5, and we get x equals 2. So let's plug that back in to see if it makes sense. If we go to the top, we'd have log of 10 minus log of 1. Log of 10 is, log base 10 of 10 would be 1. Log of 1, anything of that is 0, so 1 minus 0 is 1. It works. Okay, here's one that looks very similar, but it's actually a little bit tougher. So we have log 6 plus log 6, so we've got an addition. So remember, that's going to mean we have log 6 of x minus 3 times x plus 6. And that's going to equal to 2. So if we use our crisscross rule, we'd have 6 to the power of 2 equals x minus 3 times x plus 6. And simplify that a bit further, we get 36 equals x squared plus 6x minus 3x minus 18 if we FOIL that out. So now what we want to do is make it a quadratic, so we'd have 0 equals x squared plus 3x minus 54. And we can solve that by factoring. We'd have plus 9 and minus 6. So our solutions should be minus 9 and positive 6. Okay, so here's where you want to be a little bit careful. You want to make sure you always double check those answers. So if we plug them in, let's start with the plus 6. So if we go log 6 of 6 minus 3 would be 3. We go log 6 of 6 plus 6, which would be 12. And let's use the rule of combining those. That'd give us log 6 of 3 times 12 would be 36. Log 6 of 6 is 2. So that's good. So 6 definitely works. So let's try this with negative 9. So we'd have log 6 minus 9 minus 3 would be negative 12. We have log 6 of minus 9 plus 6 would be negative 3. And if we use the same rule, we could say, well, we're adding, so it would be negative 12 times negative 3 would be 36. Log 6 of 6 is indeed 2. But what we've got to be careful of is log 6 of negative 12 actually doesn't work. So on your calculator, if you're not sure, you can actually type that in, go log of negative 12 and divide that by log 6 and do that on your calculator. It gives you error. And the reason is we can't do log of negative 12. Remember, our log graphs, our basic log graph, is only for values greater than 0. So because we can't do negatives, that means we can't have a negative answer, so that negative 9 is a non-valid solution. So it's extraneous, so we just say our solution then is just 6. So it's a good idea to plug these in, and if you actually were to graph this one, for whatever reason, whatever the graph would look like, if we actually graph this, we would just get that one intersection point at 6. We wouldn't get both of them. So it's worth it taking your time just to double check to make sure both answers indeed work. Okay, so here's a few where they're written as an exponent, but we can now actually solve these. So before, we couldn't get this. We couldn't get 200 to be 5 to the power of something. But now we can actually solve these fairly easily. Rewrite it as log 5, 200 equals x. So we can actually divide these out. So we'd have log 200 over log 5. And that's an exact solution, so we could leave it like that. Or if we wanted to get the decimal, we just type in log 200 divided by log 5, and we get an answer of approximately 3.29. So either exact or decimal answers, depending on the question. Solve it however. So here's another one. Looks a little bit more complicated, but it'll work the same. So in this case, we'd have 8, so log base 8 of 15,109 equals 2x minus 3. So we know this left side, we can actually simplify that to be log 15,109 divided by log 8. That's going to equal to 2x minus 3. And our exact solution would be, we would have to add 3, so we'd go log 15,109 divided by log 8. That's just going to be some sort of decimal. We would add 3 to that, and then we'd end up dividing by 2. So that would be our exact answer, but if we wanted the decimal, it's pretty easy to do. Just plug that all in. So go log 15,109 divided by log 8. So that works out to 4.6. So 4.6 plus 3 would give us 7.6 divided by 2. We get 3.81 roughly. Okay, so sometimes the exact solutions are a little bit bulky because we're dealing with logs, but whether you write the exact or the decimal, it really doesn't matter. Okay, here's another one that looks a little bit more complicated, but it actually works out almost the same. So you want to crisscross these two, so just pick one side or the other, it doesn't matter which one. So let's leave the left-hand side. So we'd have log base 3, and now that's going to be 7 to the x plus 1, and that's going to equal to 2x. So we have all of this, so now we have that rule, if we have an exponent, let's bring it down in front. So let's do that first. So we'd have x plus 1 times log 3 of 7. So we want to solve it for x, so we could actually FOIL these out. So we'd have x times log 3 of 7, and then we'd also have 1 times log 3 of 7. So in terms of an exact solution, this is what we would get. So it's a little bit harder to do this one exact, but I'll continue with it just so you can kind of see how it would work. So now what we'd have to do is we'd have to actually bring the x log 3 to the other side. And we could actually common factor those out. So we'd have x times 2 minus log 3 of 7. And we could divide those out. So your x would equal log 3 of 7 divided by 2 minus log 3 of 7. So that's the exact solution. Pretty tough to do that. Normally a decimal answer is totally fine. So if we actually figure out what log 3 of 7 is, if we go log 7 divided by log 3, we get 1.77. So as a decimal, it would be a lot easier to solve it from here. So if we go 1.77 times x plus 1 equals 2x, FOIL that out, and subtract the 1.77x, so we get 1.77 equals 0.23x. So 1.77 divided by 0.23, we end up getting 7.7. So that's what all of this would equal as an exact value. It would be 7.7 as a decimal. Okay, so be careful with exact. They tend to get a little bit confusing, but just follow normal rules and you should be fine. Okay, let's do one last word problem. So here we've got a town that has a population of 12,468. It's going to grow 2%, and we want to know certain questions after that. So first thing, figure out your equation. So just like we did before, our 12,468 would be like our A value, our starting value. If we grow 2%, we'd write that as 1.02. And we'd have x as being our number of years. So the first question, pretty easy. We just got to plug in an 8. So go 12,468 times 1.02 to the 8. So we can just type that in directly. We don't have to do any rearranging. So if we do all that, we get 14,608. So after 8 years, our population is now 14,608. The second part of the question is a little bit harder because we have 20,000 equals 12,468 times 1.02 to the x. So we're looking for x this time. So first step would be divide by the 12,468. And let's just do that as a decimal. So 20,000 divided by 12,468 gives us 1.604 equals 1.02 to the x. And this one we can solve it by doing logs. We could rearrange it, do our crisscross rule, but here's another little trick that comes in handy. When you get it to a situation like this, we can actually just do the log of both sides. Just like on a normal equation, you can square root both sides, you could double it, you could subtract on both sides, whatever the case is. So in this case, if we just put a log in front of both numbers, so we'd have log 1.604, we'd have log 1.02 to the x, and then we can use that rule where we can bring that x down in front. So we'd have log 1.604 equals x times log 102, and then we can just divide by the 102. So we just get log 1.604 divided by log 1.02, that's going to equal x, which would be the same. If we actually rearrange this equation using the crisscross idea, you'd have log base would be 1.02, crisscross would have 1.604 equals x, and then from there we would divide it out anyway. So there's a couple different ways of attacking these, we get the same solution either way. So if we actually do that, if we go log of 1.604, divide that by log 1.02, we actually get 23.86 years. So roughly 23.9, or about approximately 24 years, would be when that population would hit 20,000 people. And that's all.